be with Elanga University in this lecture, and to share on biosignal processing. That's the topic given in healthcare application. What I'm going to orientate my lecture today towards how why biosignal is being challenged for students, even though they have actually have good exposure in what we call signal processing. They've taken DSP, digital signal processing, and they have a grip of mathematics, and they also have a grip of what we call as other filtering techniques, and all these in their undergraduate. But when they come to postgraduate, what makes them feel biosignal processing or biomedical engineering, it's a little more challenging compared to they picking up a master's or PhD program in signal processing, which is very generic in terms like they design filters, they take up signals which is from the industry or other type of signals compared to biosignals. What really makes these a challenge in them? I think the very first point here is the interdisciplinary. Okay, when we talk about single discipline, it is always much easier to go on working on something and saying that, okay, I'm looking into a single discipline. I have the knowledge, domain knowledge, and I have the technical knowledge from the same discipline. But then the moment they cross a little and they move into multidiscipline, which was a practice, I think, back in until 2005, 2006, until we hear the word big data and data science, the approach was very much multidiscipline, where even though we work on biosignals, we as engineers, when we work with the medical team or the healthcare team, we still do our part as an engineer, and we tend not to get too much into the territory of the biological problem, which normally handled by the medical team. But then beyond, when big data and data science is introduced, what really happened is now there's time that the shifting, from multidiscipline to an interdiscipline. So when it comes to interdiscipline, now we are looking at beyond domain limits, beyond discipline limits. The expectation is the individual who's taking up a work in biosignal need to understand the physiology, the anatomy, and the biological needs of those signals to really understand or to process to achieve the level of expectation in the research. And moreover, now we are even looking at moving from interdiscipline into transdiscipline. When we talk about transdiscipline, we really blend something into a very well-blended solution. For example, now, if I am working, I'm using ECG, for example, our ECG signal, my application is for someone to wear a ECG device, single lead, all the time, and this single lead ECG going to be a monitor for a patient who has been identified as to have atrial fibrillation. So it's like until the final product where it is like, I have to look into the device, I have to look into the signal processing, I have to look into the human acceptance, and I need to look into the processing where the final decision made real time, where the patients wear the device. So how do I really position myself, and how can I become a real biomedical engineer? This is the challenge now. The next is the team, making the team, getting the team to come together, the medical team, the technical team, the computing team where they need to do the mobile apps and so on, and also the social scientists who is going to get the humanity part to work. With all these, how a signal processing engineer is going to position himself to satisfy the different needs from the different domain people, because you are the final decision maker. Your signal processing has to work. You must be able to process the ECG signal and make it to detect the atrial fibrillation presence, and this detection algorithm need to be understood by the programmer to program it, and by the hardware maker to communicate the APIs, the application programming interface need to work to integrate all these into a final product. So you are the brain. So there's so much pressure on the brain, because the brain has to think every different part of this team, how they're going to adapt your algorithm to make the entire product work. So this is the real challenge faced by the biosignal processing team, especially the engineers who is going to process the biosignal. Okay, let me share my slide. I hope I've given some idea to the audience today to really look at how and why we are going through this session today. Okay. Okay, the slide is visible to everyone.
Yes, Dr. Kalai, yes, already.
Okay. All right. So the topic for today is biosignals and biosignal processing and healthcare applications. So this is the topic. So I gave you the opening to get you a little understanding on what really why we are in this lecture today, right? So when we talk about healthcare first, let's just have a simple overview here and look at this this whole thing. All right, sorry. Okay, what is really healthcare application? What we really mean by when we say healthcare application or healthcare problems that I'm going to handle, and how much it is really related to the biosignals, and how it's really needs the support from the biosignal team to solve the problems. So I put up here the top 10 custom healthcare application, and we look at the first one here is the online patient portal, the disease management, the patient condition reporting, health and wellness management, diagnosis reporting, inventory management, research and development databases, digital transformation and productivity, knowledge-based system, and laboratory management. These are the top 10 custom healthcare application which has been popular lately. And if we look at each one of them, when we say online patient portal, of course, most application today, or when talk about online patient portal, it is still at a very preliminary stage where the patients actually are able to record their information. And I think the pandemic has opened the door for the online patient portal to have online consultation with the doctors. But what is happening at research level is we are trying to get patients' body signals to be recorded in this online portal for the monitoring by the doctors. And when the patient have an appointment, the doctors can make a better judgment or better treatment decision to provide them with more personalized treatment and prescription. Same goes to disease management. There's lots and lots of work around the world is going on, especially on diabetes, where we are really looking at recording patients' progress, on daily progress and the sugar condition. Of course, currently the gold standard is blood measurement, but there is a lot of effort being put in different type of signal tapping into disease management, especially in diabetes at the moment. Same goes on patient condition reporting, health, wellness, and diagnostic report, and the rest of them, where we are trying to always get a real-time or near real-time body signals to be recorded, so we can personalize the treatment. And these bring us to the next step, where we call as treatment compliance. And the magic word for any type of treatment in hospital today is the treatment compliance. If the patient can comply to the treatment that provided or prescribed by the medical practitioners, highly we have possibility to have a complete recovery. So the magic word is treatment compliance. And most of the work that we work around biosignal is towards providing a more accurate and personalized condition of the patient at any point of time, to ensure that the treatment prescription can be personalized and also accurate to the individual. So that is what we are looking at. So in this process, when we talk about custom healthcare application, how do we develop healthcare application? What are the steps actually when we want to develop such applications? Normally, like I put here, is TRL1 to TRL8. Why? The reason I actually position the TRL1 to TRL8 here, to show that when we want to develop an healthcare application, if we start at technology readiness level 1, we will progress up to technology readiness level 8 to complete the application. When we go to level 9, it means that our product is already in the market. That is the final stage. From the completion of the work to go into the market application, that will be the final stage, which is TRL9. So in this process of TRL1 to 8, what are the steps really involved? We will have to define the target audience and also what are the requirement, and then we go on the craft clickable prototype. So it means we want to develop the prototype, build, integrate, and make it secure, analyze usage metrics, and then scroll down and find out, go down to the market and do the testing and find out what is exactly happened. So our whole work today, we will be focusing on the step 2. The step 2 is where the biosignal processing will take place. So it is like kind of after TRL1 in step 1, TRL2 and TRL3, and will be practically working on the prototyping, which heavily involved in our biosignal processing and the algorithm development. Right. So role of biosignals in healthcare application. What is the real role of biosignal in healthcare application? Is patient monitoring, is the critical care. Yeah, that is where actually it plays a big role. Then we have these ICU or the coma patients and ICU conditions, where we are looking at biosignals able to play a good role. Disease detection or diagnosis. Excuse me, I think somebody's mic is on.
Yeah, maybe yeah. Already
yeah, right. Thank you. Then we have the heart signal, which is ECG, brain signal, EEG, muscle signals, EMG, and etc. We also have a lot of signal processing happens at the preventive healthcare, human machine interfacing, HMI, and BCI, where we have also many application on BCI that works with what brain computer interface, brain machine interface, and human machine interface. These are all those activities very much working on today, if we look at on rehabilitation and mental health. And then we have the controlling of wheelchair, prosthetic arm, and so on the rehabilitation. And we also look at treatment and rehabilitation as part of biosignal applications. And last but not least, basic understanding of the organs, physiology, and function. For example, that's people who work on heart rate, people work on brain, people who work on kidney, and people who now start working on pancreas and liver. So different type of signals are tapped, physiological activity being tapped from these organs, and those signals which is tapped and pre-processed and further processed, analyzed and classified to look at the organ condition. So these are the entire range of potential work to be done in biosignals in healthcare application. So again, back to my introduction just now, how do you position yourself in big data and data science now? Because there is a little confusion again. I think what happened in 1995 when IT came very fast into ASEAN country, a lot of people thought it is only for the computer scientists. It is not for the engineers. And it is, and what happened in countries like us, we start focusing to look into developing our manpower in programming. And again, now I could see the same trend. People, industries were coming to ASEAN country, trying to push and emphasize again that we need to learn R, we need to learn machine learning, deep learning, and that's about it. My question to all of you, if you are just doing that, is it possible for you to position yourself in these type of applications, healthcare applications? It is definitely not. If you're just doing the front end part of it, what about the back end? Who is going? So now what's going to happen? This back end work is again going to happen in the Western world. They're going to extract the information and put it on into the online systems, and we're going to develop algorithms to process that without knowing what we are processing, but our algorithm is going to be fantastic and intelligent, and it's going to give a lot of good classification, good clustering, good decision making in prediction and preventive and so on. And this is going to go back into the pool, and the final application is all going to come to us by package from the Western world, and we're going to pay for it again. So unless we master ourselves in biosignals and we know how to extract, how to process those signals, understand the signals, and also images, we should not leave them alone, also the images, and we need to really know how to do this. And to do this, we not only must understand engineering and what is digital signal processing, but we also need to understand the nature of these biosignals. To understand the nature of the biosignals, we need to understand the anatomy and physiology of human body. So this is the entire needs in this scope that we're going to make the hit that I'm going to be a real successful biosignal engineer. Right, let's look at the challenges with biosignal. What makes it complex and what makes it tough? Yeah, very low signal to noise ratio. That's number one. How do I going to manage this, and how am I going to extract the information that I want when I have this situation? Non-stationary and non-linearity properties of biosignals. Most definitely, human body is not stationary and it's not linear. So the signals that we tap from human body will be non-stationary and non-linear in terms of its properties. So how, and I can't be using standard processing techniques when it comes to when I'm handling a non-stationary and non-linear signals. So this is my second challenge. The third challenge is diverse type of noise, because when we talk about human body, when I want to tap a particular signal, my other parts of body is also functioning. That's why you see, whenever we say we want a good signal, we prefer our patients to sleep. So when they go to sleep, many of their activities are not at the height, so that you get less noise. But at the same time, when body is, if they are sleeping, we may not get what we want in the signals too. So here we have challenge. So we need to also have a good understanding before even we we record the signal. What should be the best position of my patients or my subjects participating in my study? Should they be sleeping, or should they be resting, or should they be in supine position, or should they be sitting? If they sit out, should they sit? Are they supposed to sit 90 degrees? Or should I give them a rest at a 45 degrees? So how exactly I want, or they should stand, or they should squat down, or they should be exercising. So it's very, very important to actually to make the decision what the patient's position should be even before we record the signal. That will also help us very much in our processing. Next, look at the noise and artifacts. Overlap both in spectral and temporal domain. So here we may see them in both spectral and temporal domain. So when we do our processing, we should not say only look at one aspect and we say, okay, I've removed the noise or the artifacts, I'm done. But on the other domain, you did not really look into, or you didn't even bother to process in spectral, in spectral or in temporal domain. So in this case, you may not extract the best features of what you want for your further processing. And lastly, we have the false alarms and errors can mislead the diagnosis, treatment, or control of any external device. The environment that we do recording, I have a very interesting challenge. We were recording in a hall, and the device was plugged into the power at the wall in the hall. And when I looked at the signal, it was so noisy. It was like really bad. And we start checking what was wrong. Is our device faulty and all that? And lastly, we said, okay, let's change the plug point, move it to another place. When we moved, that was okay. So there was a power interference from the plug point itself. There was a leakage. So such things also need to be looked, to be verified. Are we really in a good, also important to look around what type of device. You may have a very loud speaker next to it, something magnetic around that area, all these type of interference will also provide you the false alarm and error. So these are the very important aspect that you need to look at when you into biomedical signals. It starts from the time that you start designing your problem and deciding your data collection and your device, and how and where and when, who's the patient, how they should be positioned. Every single thing is important before we come to the signal processing itself. And I think what makes, when I looked at 70% of the papers published today, they use a database which is on internet, like Physionet and many other. I think the number of database now, when I was studying, the only reliable was Physionet. But today I come across about more than 20 or 25 reliable databases for biomedical data. They have a lot of data. Of course, you don't get patient details and the rest of the input, but you have the signal, you have the basic information that you need to do the processing, especially when your focus is on deep learning. It is like very much prepared and made ready for deep learning applications, application development. So that is about 70% of the papers published around the world today. They are using these open databases. And there is many reasons behind it. I think this is a repeat of a scenario which happened in 95 up to 2003, 2004, even to 2005 in the IT sector. So we are now looking at the similar thing happening in the data science and artificial intelligence, simulation, all these pillar of the IR 4.0, where they actually need a lot of people to try their database and try their application and develop solution, especially in deep learning. So the more and more people working on this will actually make deep learning concept and algorithm development more stronger for whoever has actually introduced it, so they can make it as a benchmark and package their solution into products and push it back into the market, like what happened earlier, like what Oracle did. That is what Oracle did. And finally, Oracle became the leader, the master of the industry for databases. That's what, again, IBM did. So all of them at the same approach. Now is round 2 or round 3 in the IR. When IR 3.0 was introduced, it's completely automation using computers. So that's what the approach was same. And today with IR 4.0, which is a knowledge-based automation, I define this IR 4.0 as a knowledge-based automation, where they use knowledge to make the automation more intelligent. Of course, with 5G and all that, we have this wireless technology, which makes things more robust. Without wire, we can actually communicate data around the world. So that makes it more interesting. And we can, when we talk about knowledge, where the knowledge come from, knowledge can come from any type of data, not only text, it can come from image, signal, speech, even movement of people, your face expression, your smiles, your eye expression, anything can be a data, any objects. What you share in WhatsApp, what you share in Instagram, the TikTok videos that we are launching in our country, which actually reflect what type of people living in Malaysia. They will just need to collect all our TikTok videos and review that video and analyze the video, and they can classify what type of people are living in Malaysia, what type of people living in Indonesia, what product I should sell in Indonesia or Malaysia, who will buy, what is my market size, who will be attracted to my products. Even they want to introduce a drug or what we call it, the pharmaceutical products, who will buy my vitamin C. What is my market size of vitamin C in Indonesia or in Malaysia? It is very much easy, just can use the TikTok videos and start predicting. So this is like, it's all knowledge. Everything that we throw onto the mass media today is knowledge. So this type of data is going to be very valuable to the marketing team. And this is what is being focused now. Same goes on biomedical application. Biomedical signals are great things, and that's going to have lots and lots of value. So what is actually biosignal? Biosignal, bio and signal. So it's living object with function that carries information about the behavior or the states of the living objects. So I've put in like on a human, that's so many different type of signal can be acquired. ECG, EEG, EMG, respiration, blood gas, blood pressure, interface pressure, resistance, temperature, and many, many more type of signals can be tapped from any human body. Practically, we can like really monitor ourselves, what's really going on and what is the condition of everything in our body, every organ, our vessels, our muscles, our neurals, and everything. So this is completely going to give, and when we combine this is where we can predict our health conditions. So that's going to make a biosignal very interesting. Right. Again here, what is biosignal? And continue. Anything related to life. The simplest example is temperature. By monitoring someone's temperature, we can definitely know whether they're having fever or not. Are they in the hyperthermia loop or hypothermia loop or thermoregulation? That's 4 different biomarkers can be what we call it, can be produced or predicted from just monitoring someone's body temperature. So if we have a device which we can actually fix on someone, we have, let's assume we have a temperature sensor, which is just like a patch. One day, one in the morning, let them put it on, and the next day after taking bath, they put the new one, and we can like continuously monitor the temperature. So we can actually look at the person's condition, whether they are hypothermia and hypothermia and regulation. And there is findings or papers published showing that if 1 or even 0.5 degree of our body temperature dropped, there is a potential for us to get cancer. So a drop of body temperature has a very close relationship, or there is a potential for this individual to get a cancer disease. So if we monitor and we could see there is a change, there is an indication of drop, so we actually can alert the person and say, now it's time for you to look into your temperature and what is the cause that your temperature is dropping. So when the papers and indicated temperature drop can caused by hormonal change, hormonal activities, enzyme activity in your body, and also electrolytes activity change in your body. So those things will be tested, and it can be regulated, it can be recovered, and we can actually, most probably we can prevent this person from going into the cancer state. So these are interesting applications, but it's a very simple device. It's just a temperature. But what is important here is your analysis. How do you going to have this prediction done? How are you going to come up with an algorithm to use a temperature data to look into the fever condition? Is quite straightforward about hypothermia, and thermoregulation. It's not simply minusing and adding. That would be a pattern where you need to plot those signal. I mean, temperature, maybe you have to plot it every hour in a day, and then you look at the pattern for daily. What is the drop? What is the move? How it's moving? And are we going to use an average, or are you going to take a median, or are you going to take the standard deviation or variance as your indicators for you to calculate or predict the hypothermia and hypothermia condition? We may have that value, but to validate the value, we need other statistical processing to actually come to a point where we can make a decision. So biosignals are non-electrical, also can be a non-electrical signal that is capable of being monitored for biological activities. And even this is not really recorded as signal, but the daily plot actually can be what we call it as extrapolated to be a signal, to look like a signal, and this is being used for further processing as a signal. Right. And how to record biological signal? Of course, I put a very simple device here and showing what are the potential recording signals: acceleration, accelerometer, blood sensor for SpO2, sphygmomanometer, and then we also have the body temperature, we have a glucometer, we have the ECG, we have the breathing, we have the sweating, of course, with all other signals in the category of biosignal. Right. So now, how to process biological signals? Again, we want to look at the most of biomedical signals are currently recorded using computer and stored in digital format for further analysis. So we already have the first part of the challenge not there, but again, I'm still touching that in the following slide, where we have analog signal. What happens when we have an analog signal? What should I do? How am I going to go through my processing? Yeah. Second, the process of converting continuous time signal, which is analog, into discrete time signal, which is digital, is called the analog to digital conversion, A to D. And then the third is the reverse process of reconstructing an analog signal from its discrete time samples, is known as digital to analog. There is situation that is in certain type of application or needs, we may need the signal in the analog form for us to extract or for us to analyze, to look at the statistical reliability and so on. We may need it in the form of analog instead of digital. So those are the early processing part that we need to understand about biosignals. So it's a very direct, simple, straightforward A to D and we use the DSP, continuous time signal, to discrete time signal, and discrete time signal to continuous time signal. It just works vice versa. And there are three components in analog to digital converter. We use continuous to discrete converter, then we use the quantizer, and then we use the encoder. And this is where we get the binary code words. So when we look at that, first input a real value function denotes as, of course, x at a time of continuous variable, where t, which is time, and then continuous to digital converter converts into the discrete time sequence by extracting the value at integer multiples of sampling period. So we need to always be aware of our sampling. We need to understand how to decide on this, and we always must know the device that we use, what is the sampling rate. Yeah, maps the continuous amplitude into a discrete set of amplitude, and the quantization process is defined by the number of bits and also the quantization interval. So this will actually ensure the accuracies. And finally, the encoder produces a sequence of binary code words. Of course, it's very interesting to go into detail of the mathematics, understand the mathematics, and code it ourselves. But definitely today, with the technology and on all the tools like MATLAB and so on, students just using the what we call it, the readily available tools to do it. And this is one of the reasons why when you want to write a Q1 or Q2 journals, you do not have a good grip of what is happening behind all this. Because everything is tools. You just go into the toolbox, you call the toolbox, you upload, you import the signal, and then you just press the buttons and you get the whole thing converted, and you know, okay, now I have it in the form that I want. But what is really happening at the back is hardly known, hardly understood. So when you want to write a Q1, Q2 paper, they do not want you to just use the toolbox. And most of the time, they expect you to do some modification, or you introduce some new techniques, or you impart or embed a different step, or you go beyond certain steps, because toolbox are standard. Yeah. So you want to make the difference there, you need to know the mathematical behind this application. So in Q1, Q2 papers, if you are doing your master's or PhD in signal processing, so you definitely want to publish in a signal processing journal. When you want to publish in signal processing journal, which is Q1, Q2, you cannot be processing your results using MATLAB alone. This is definitely not accepted in those journals. They would like to see your steps in mathematics and what you modify. How do you fine tune the steps with some additional data structures, or you change the sequence, or you put in a different sorting techniques into this applications. So this is what is expected. If it's not, then it's hard for us. Most of those type of tool-based application is easily published in Scopus or WOS now. So this is the difference it makes. Yeah, right. Now, analog to digital conversion, like what we say, it's from analog, it goes to digital, then the sample to quantized. So these are the steps involved. And I know this can be straight away done in our MATLAB toolbox. But how you're going to understand what, if it's a standard toolbox, if you have 10 papers, 20 papers, 30 papers, everybody is using the toolbox. So your process is the same. What are you special about in your work? What different you make? How it going, you are using different signal, or you are using different group of patients. We are not social scientists or medical doctor just to change our sample size or sample type and then we can publish it again. No, because we are the technology people. We need to have modification or change or innovation in our technology, in our processing, in our signal conversion. When I convert my analog to digital, how do I get a more specific, more detailed, more, I can say that my signal has better physiological features. I did not lose as many features compared to the common toolbox conversion. So these are the things that they are looking forward for in the Q1, Q2 papers, right? Now we are moving in, once we have done either from digital to analog, here we are looking into digital. So signal processing in biosignal analysis and modeling, I'm going to approach through what is, first I would like to introduce you what are the traditional signal processing techniques that always being done in any biosignals. There are 4 steps. The first step is signal processing. Second step is feature extraction. Third step is feature selection. Fourth step is classification. That's where we end. Normally, we can classify, we can differentiate the type of patient that based on their disease or based on their characteristic that we are looking for. So if you look at the signal processing, it is not just a single thing we do, especially in biosignals. The very first thing, of course, we need to do the denoising techniques. So we need to be selective. Are we going to use pass filters or resampling or ANC or SANC? Which one is suitable for our signal? How do I make this decision? Yeah. So this decision, most of the time we make based on a good literature review. So when you do your literature review, you must also make sure that you are actually reading papers from a reliable journals. So otherwise you will make the same mistakes, which is already in the paper. So you're not going to go anywhere. So decision on selecting the techniques is very much dependent. Currently, we are still depending, unless your lab is a very established lab, you already have research 20 years, you have experienced researchers, and they already recorded from the past that if this type of signal for this type of study, then this is the package of denoising techniques that we should use. So then we have a very quick move that we can make. Otherwise, we still have to go back to our literature review to make our decision, which will be the best and the closest to our solution. Next will be the signal enhancement. If we choose to do the MED or spectral catalysis or any type, how do I enhance my signal? My signal needs some enhancement. And then signal decomposition, which we normally do with wavelet or EEMD. And with that, now my signal is ready to go into my feature extraction. Here feature extraction, in traditional method, a lot of N-craft features are done, like using statistical based features, like what I told you just now, mean, median, standard deviation, variance, and many more, and knowledge-based features. So we look at some experts are there, they can tell you exactly what are the features to be used in this particular signal. Then we also have feature function techniques like, that should be a bracket. Principal component analysis, PCA, or independent component analysis. Okay. What is the advantage and disadvantage using PCA and ICA? They normally will cluster the features into a package, and they will maybe take 2-3 features together and say, okay, these, because we really cannot single out the features from in the signal by using PCA and ICA. So they will actually provide us a ready processed kind of components. Say this is component 1, 2, 3, 4, 5, 6, and these are their strength. And it's very, very hard from my experience to relate them to the physiological features of the biosignal. Because when we understand, like for ECG, we have P, Q, R, S, and T. So how do I relate the P to components which is given by the PCA or ICA? Which one belongs to which? it's really hard. I've tried many times in my work, and I've never successful to match them. Many techniques and many effort I've put in for, I think, about 5-6 years, but we did not achieve how to break up this and relate it back to the physiological of the biosignal. That's the challenge here. So next is feature selection. Feature selection, once we have number of features, like say you have 15 or 20 features, and you want to know which out of these 20, what I'm going to use. If statistically, normally they use effect analysis to determine which features as the strong standing to be selected to go into the classification. So in signal processing, feature selection can be done by divergence, FDR, JE, and different type of feature evaluation tools. And so we have a feature subset selection by using exhaustive search or sequential forward search, or sequential backward search. That is also a technique to be used in the feature selection. And finally, in our classification, most of the time we end up using machine learning algorithms. You can see, like, if you have 200 papers, almost about 150 papers will be using AN or KNN, and also SVM or random forest RF. So these are the commonly used machine learning algorithms to do classification. So this is the 4 steps traditionally used in signal processing of most of the biosignals. And what I do see most of the time, that feature selection part is missing. That was not an approach. If you get 20, what most students will do is they put all the 20 into the classifier and then trying to classify to get the best classification score. So that is what happens. And the feature selection normally can be done if you have a good understanding of your physiology of the signals that you are using. If you don't have the knowledge about the physiology of the signal, it's hard for you to make a decision which features should be retained and which should be removed. So this is another huge challenge here. So to ease, it's not clear. To ease the types of biosignal here, the processing, it is also nice to know whether they are determined, they are the type under the determined type or the stochastic type. That's going to help us quite a bit in our decision making to choose the type of processing techniques that we want to put in each one of the 4 compartments that we saw, that which normally in the traditional method is not being applied. So when I determined when it comes under determined, we have also 3 types there: periodic, quasi-periodic, and transient. So we need to know what is mean by a periodic signal. So signals wavelength is repeated periodically. It means they are very consistent. They have the same type of signal which is repeated, which hardly found in biosignal. That's what I mentioned just now. Biosignals from human body, we are not monotonous, we are different, we are intra and inter of our body activities are always different. Each one of us has a unique set of signals for our own body. That's why biosignal can also be a good biometrics. But even in our own body, they may not consistent all the time. So that makes it very challenging to have biosignal as a biometrics. Out of all those different type of signals in our body, I think the most stable is ECG, consistent. But yet ECG can also change if there is mental stress or you are shocked over something. So it is, till today, it's very hard to use biosignal as the biometrics for security. Right. Enda, why are you scratching the screen? Right. So then we look at quasi-periodic, where we have the wave shapes is repeated almost periodically, like ECG. And then we also have the transient, where the wavelength occurs only once. And under the stochastic, we can see stationary and non-stationary. Examples of stationary properties, do not change in time, which is like the alpha waves. And also for non-stationary, the good example is EEG or EMG, so which as the properties change during the time. So these are some of the type, and which will help us to select what are the type of processing that we should be selecting. All right. Then we another information which will be helpful to us will be the analog to digital conversion, where we look at the bandwidth information, amplitude, range, and quantization of the of some frequency used in the biosignals. So different biosignals will have different bandwidth, amplitude, and quantization. So this could be a good reference also in our decision making when it comes to selecting the techniques, the processing techniques, the noise removal and feature extraction, feature selection, and classifier. So they will be very useful information for us to do the selection of our methods to process our signal. Right. So analog to digital conversion, for example, the effect of the sampling frequencies. So sampling frequency will definitely a good input. It has to be included when we want to do the analog to digital conversion. And that actually provides us, eliminates or help us not to eliminate or lose the physiological features of the signals when we do the conversion, and make sure that our converted signal is rich with the information that we require for further processing. Now, when signal amplitude properties, and this is also another very important feature that we need to understand before we go into our signal analysis. Amplitude distribution function will give you a very good understanding of the of your signal, and to understand your signal and their nature, and how they are distributed, what they carries, and how you can actually use them to make a decision in the problems that you are looking at. Because if the health problem is going to relate to the amplitude function, then amplitude can be a feature that you can consider for your processing or for your classifier design. So this is how we want to look at individual properties of the signal. So the first one we look at here is the signal amplitude. So you can also, it's a bit small on the other side, you know, when I have the example of 2D amplitude distribution, when you can see that signals are closer, further, so that how they actually shift in the space. So that is also can be a good indicator. On this side is the signal amplitude for vectorcardiogram. So when we look at vectorcardiogram, when the signals are, you know, the amplitude change and the amplitude differ, you can see on the B plot how the whole thing has been plotted. So this type of plotting also can be used for as a classification input. So you can classify people by the pattern of your signal amplitude properties. Yeah. Then we go another example here, two-dimensional amplitude for DDS for EEG amplitude and RR intervals. So you can look at how Holter RR and the EEG it's differ when we are using these two different type of signals amplitude properties as input to the classifier. It is a potential. When n is 0, when n is 1, when n is 2, what are the values we are getting. The plots itself can be an input. Same goes on the EEG, when we have the different type of signals and different analysis done based on an amplitude. It can be a feature that we can use for further processing. Okay, then we have the frequency spectra and filtering. And frequency spectra and filtering also, there are the techniques that we normally use. Examples here, we have 3 biology signal with their frequency spectra. If you look at the different signals, how the spectra is looks like, and from this spectrum, now how you can actually extract further features to be used for your classifier. So this is another method, technique to be used. And on this side, we have the frequency component. And when I use the first, third, and fifth harmonic, what is my, and I'm using 2 different, first I'm looking at block shape signal, and second one we have sawtooth signal, and how do they help us to, to extract the features that we want for the processing. So all these selection, normally, if you ask me, how do I decide which one I'm going to use? My answer again, the literature review is the best. So you need to read papers which is closest. First, the signal must be the same, and they have the closest approach to what you want to do. So based on that, normally you can identify the details of those application that is suitable for your processing. And then you can do a modification. Once you establish the fundamental, then you start looking at your own needs and start adjusting the parameters accordingly, modifying the mathematics accordingly, and then achieve the optimum outcome or output that you are looking for. Right. Another technique here on the processing will be definitely digital filter design, which now I think MATLAB almost made everybody not doing this anymore, only using their toolbox. Again, in digital filters design, what I'm really looking for. So biomedical signals such as heart sounds, electrocardiogram, EEG are much likely to be inferred by various factors such as muscle and joint movement, breathing sound, environment noise, as well as power line interfaces. So what is really digital filters design is going to assist you? The ideal digital filter is designed to pass these signal components of certain frequency without any distortion. So that's what we are looking at. So when we want to target a particular frequency in our signal, and we want to extract features related to that known frequency, then it's nice to have a digital filter design. Ideal digital filters as a frequency response of value equal to one of these frequencies, and frequency response of value equal to 0 at all other frequencies to totally block the signal components with those frequencies. So you can beautifully extract what you really want at certain frequencies. And you know this for exact purpose. Maybe like in the case of EEG, if we are working on epilepsy, normally the medical practitioners, the neurologists, will be able to use some indication or some value that they said, okay, this is the range, or this is the value that we're really looking for, the frequency that we are looking for to extract the information that we want. I do see this also among the ophthalmologists and the eye doctors. They also now start using signals around the eyes to support their decision making. And they have also a standard frequency that they want to look at what's happening at that particular frequency. So these make things more interesting in biosignal processing. And these are the ideal filters. We have the low pass, with the high pass, we have the band pass and band stop. This is the normal ideal filters. So like what I told you, if you use these standard filters and you're trying to publish in Q1, Q2, it's not possible. So it's like yeah, it's known, it's everybody. But how do you going to make an hybrid? Or you're going to use them together and you're going to come up in an algorithm written in first step. I did use my high pass filter, and then now I'm using my band stop, and you justify why are you doing this and what are you looking for in your work, what is so special about the feature that or the frequency that you're looking for that you need to use high pass, and then you apply band stop on the work that on the signal that you're using. So this may justify the IAQ journals for you, and in that must be a very good rationale and how this is really workable in your work. It is not just because we want to do some difference. We purposely use high pass and then band stop. But then if I only use a band stop without a high pass, I still can get the same results. That is not the right, because the reviewers normally, these good journals reviewers, they are really aware of what's happening around them, and they definitely want a good feedback from you. Right, filter specification. So when you want to design a filter, what should you be doing? So filter specification includes pass band cutoff frequency. That's the first thing. The stop band cutoff frequency, and then the pass deviation and the stop band deviation. So figure shows the filter specification for a low pass filter. From my experience, what I see among the researchers, when they read the paper, they always miss these good points. When they do review, they would have read like 20, 30, 40, 50 papers. But when I said, okay, what most papers use as the pass band deviation, they'll be like, oh, that's important. I did not note it down. So for you to go back to the 50 papers to note these down again, that's going to be an additional extra effort, 3-4 hours or 5 hours or more. So this is again comes with the planning. So to be a good biosignal processing person, I think the most important is your planning and your readiness to understand the paper. When you read the paper, you must understand what you are reading. You cannot be like assuming or thinking that, okay, I'm reading something and I know something. It is like more that you really know the details, the parameters that is required and what those papers have used. When you compile them, and finally you will see like a real pattern, and you can actually make a very good decision for your own design. So this is important. I think the reading part is the crucial part, to read and extract information from what you are reading. This is what I'm saying from just now. It's pretty easy now. You have the filter tool in MATLAB. You can plug in, but make sure that when you choose them, the type of filters and all that, don't do trial and error. We are not doing guessing game here. So make sure that you understand what you're plugging in and what is the reason you're plugging in all this data for yourself to do the filter design. So filter design in ECG, I took a simple example here. Low pass filter, eliminate noise such as the EMG and also the 50 Hertz, because normally ECG, we may capture together EMG because there's muscles around the heart. So there may be some EMG signals is part of the ECG signal. So when you do the low pass filter, you eliminate the noise, which we category as EMG and 50 Hertz power line noise. Then we have the cutoff frequency at 11 Hertz, and you have the your equations, and you have transfer function, and you can actually look at your frequency response in the IR filter or the phase response IR filter, and tune your filtering to the best that it can, and it suits your needs. So the results here we could see from the ECG to lead for normal and low pass filtered. So how much improvement you could see. Then you think, okay, they are still noisy, I need more, because most of the time ECG, they will look for the PQRS. If they can see the PQRS and you look pretty steady, then the filtering is good enough. Okay, right? Now, example for the used for the QRS detection. So when I want to do a QRS detection of ECG, we use I-pass filter, eliminate the motion artifacts, P and T. We do not want P and T because PQRST, but now I'm not interested in P and T. I want to eliminate them. So that I'm moving into high-pass filter, cutoff frequency at 5 Hertz, and the equation, then we have the transfer function. So this is like, okay, now I just need the QRS part. So I'm going to bring my window closer, and I just want that particular portion to be known to me. So that's, so you could see the rest of the part is not being managed because we are not interested. We only want the PQRS because we are looking, most probably here they were looking for the RR distance between each peak. So they are only interested in that. And why they do this, especially in the big data and the cloud and so on, this will give you a very quick processing time and feedback to the patient if they are just interested in the RR value. Yeah, because the RR value will give a good indication about your atrial fibrillation, whether you are actually you're having atrial fibrillation or you need, you looks like that it's appearing at the moment or something like that. You know, so based on your application, as what I mentioned just now, your filter design can be customized. Not the entire signal need to be processed. And this is mainly done because we want to save the processing time and also the loading and uploading. So all these contributes to the end product, whether your product is going to be very efficient and reliable and timely. So this is the basic that they want from you. They want an accurate result, but yet you don't do the processing which is not needed. Right. Okay, moving from there to biosignal analysis, the next step. Yeah, it's also come under signal processing, but now I'm not doing the removing artifacts and all that. I'm going to do feature extraction. So when we talk about, again, I use the ECG signal characteristic, relative power spectrum of QRS complex, P and T waves, and muscle noise and motion artifacts. So if you could see that we have the motion artifacts, we have the QRS complex, and we can also see the muscle noise at the bottom there, and the P and T values. So this is all having different frequencies, right? So when we want to do a QRS detection algorithm, we had low pass filter, and then we did the high pass filter, we do the differentiator, and then we'll go into scoring operation and moving average filter and the output finally. So this is a pretty standard QRS detection algorithm you'll see in most papers. This is the detail of the algorithm design, you know. So we have the band pass filter, cascaded low pass filter, and high pass filter to isolate the predominant QRS, energy centered at 10 Hertz. Energy of the QRS is between 5 to 15 Hertz. So we look around at the 10 Hertz, and the low pass filter eliminate noise such as AMG and 50 Hertz power. So that takes away that what we don't want to be there. And then the cutoff frequency is 11 Hertz. So with that, you would come where the you eliminate the motion artifacts for the P and T with the high pass filter and the cutoff frequency 5 Hertz. So you eliminate like what we saw in the previous. First, you eliminate the power line, and also you eliminate the EMG signal. Then the next step, you go and eliminate the P value and T value. So then you do a differentiation to obtain information on slope and overcome the baseline drift, which is accentuates that QRS complex relative to P and T wave. Then after that, you do the scoring. When you look at the scoring here, emphasizes the higher frequency component that attenuates the lower frequency component. So we do the scoring, we can actually look at the higher frequency and the low frequency. With that, then we move into a moving average filter, which acts as a smoother and performs a moving window integrator over the 150 millisecond. So you could see how the signal now has been, the top one is the ECG normal, and the bottom, the ECG normal after the MA filters. So we could moving average filter. So now it leaves us just the QRS and clean. Compared to the earlier one, if you look at this signal, it is not as beautiful as what we are looking at, because even the QRS has been detected clearly, but the rest of them still sitting there. And no, when you are doing further processing, you may have disturbance from that. But in this case, when you use a more accurate detector with the moving average window, you have a very clean a QRS to be detected. Okay. Here we use the ECG ventricular one, bigamy, and then EEG ventricular one, bigamy after the MA filter. So you could see how they are like eliminating all those unwanted part of the signal and also the noise, and make it very reliable. Because in this case, I'm very sure they want to look at the peak, and they are counting the distance between the peak to peak. So this is where they only interested in QRS. And here we can look at how the digitized ECG signal is being used and filtered through step by step, and finally you have what you want. You can always try this. You can download that tons of ECG signal. If you're really keen, interested to learn, you take up one signal, just repeat back all the steps and try to learn in each step by playing, changing parameters. How do you improve their processing? And this is the data from HUKM. So ECG waveform after bandpass filter, and then after moving average. So this is a real signal from a patient from the hospital, and we apply what we have applied earlier into these, and we could see that, of course, it's not as beautiful, as sharp as this one, but here we still have the peak of the QRS. And of course, we can calculate. It is just that now we need to do some normalization. So the height of the peaks are the same. On amplitude, we have normalized the amplitude, and few other work, maybe change it to the time domain. This is in frequency, and we can get a better performance and plotting of the signal. So the QRS complex is detected when the slope amplitude is within the threshold, and heart rate is calculated according to the formula below. So once they have that, then they use a formula, the standard formula to do heart rate calculation with ECG to calculate what is the heart rate for the person. Right. So I'm going to leave out the last half an hour for Q&A, but I'm not covering this today. I think it's too much, because when I saw the slide, that's another 40 slides on this. But I put here what's next to explore is wavelet transform. And what is wavelet do? Earlier, whatever we discussed just now, it uses Fourier transform. And when we use wavelet, it both do the analyzing function. But the difference here is there is a major disadvantage of Fourier transform. It captures the global frequency information, meaning frequencies that persist over an entire signal. It goes on the entire signal. And sometimes in a biological signal, halfway through, the patient start moving and restless and so on, we will not have a good signal recording. So if we don't realize and cut off, sometimes we can't cut off because we need the signal for the 2 minutes that we record. But we found that at the 40 to 50 second, the patient actually move and being restless, and we have damaged data recording there. Even we know that we have no control when we use Fourier unless we cut. But if we cut, then it will be shorter than all the other signals. Then we may not get the good results either, and we cannot process either. So in that case, wavelet transform as an alternative approach is the where it decomposes a function into a set of wavelets. So this gives us more accuracy, more room to actually ensure the accurate part of the signal is being used, and we can eliminate all those which has noise and so on to not be part of the processing. With that, we may get a better outcome and more reliable features compared to we are using Fourier transform. Right. So with that, thank you very much. And I hope I will get some questions so that we can have more input or more discussion on this.
Thank you, Dr. Kalai, for such a inspiring lecture. Now we move to Q&A session, but maybe here's also Dr. Heri Tilaksana. Maybe Dr. Heri want to say hello to you, Dr. Kalai. Is it
Sure.
already available?
Hello, can everybody hear me? I'm so sorry. I'm at home, so it's might be interfering with the other sounds. Kids, could you please bring it down? Alicia, could you please bring it down? I need to talk. Yeah, here it's as usual. So I want to say hi, and how are you, Professor Kalai?
I'm good.
Oh, thank you very much. Yeah, so we're very thankful and feeling grateful that you're very keen and happy to have the. I think this is the first we are inviting you for this DECOTA webinars from Airlangga University, right? Yeah, and also I think this is a very, very good chance for both university from Indonesian and Malaysian university to share whatever we are doing at the research or at the teaching. So it's going to be a bit improve our productivity, whatever in the term of teaching or research in both sides. And here we have Ms. Riris, and she's actually the head of school for biomedical engineering. So she's going to be more capable in this area. I can recall couples of stuff like Ms. Osma as well is very, very young and very, very potential for any research activities in biomedical engineering, while I'm actually doing a bit more physical things in spectroscopy and material science, as well as of the photonic applications. So that's kind of the two schools we need to manage at the same department, in physics department at Airlangga University. But I'm more than happy we are going to have any collaborations, any activities together with the SAMS collaborators from Malaysia, from India, from other countries, because there's kind of the target kind of we need to take into account considering all of these parameters in internationalizations. And okay, we're still learning about this. Our university is still just crank up whatever the level we are currently on. But yes, we are ready for collaboration with other, the cameras, yeah. So with other collaborators such as Professor Kalai in Malaysia. So thank you very much. What I'm going to say, representing all of the stuff in physics, and yeah, this is kind of what we're supposed to do, right?
Yes.
Yeah. Okay.
It's a good activity to exchange.
Yeah.
Yes.
Okay, we have a COVID-19. We have the limited by the borderless, because we can't travel across the border for couples of months. I think it's already 20th month since the lockdown in March last year. But there's still fortunately we can do things like this, whatever we want to. Let's say we can't do any hands-on activities. We can't go through the laboratory activities. We don't know how to get there because completely stuck and stop the access to the building, to the laboratory. But at least we still get this thing to build up the communication, to build up the engagements. And then while everything is done, and hopefully the pandemic outbreaks is already is going to be done shortly. Then we can visit across each person from Malaysia, from Indonesia. Then we are going to plan whatever the research we are planning on any scheme, in national scheme, in international scheme, because yeah, we already have a lot of grants, but we do nothing. We stuck on this situation, just stay at home, just discussing here and there. But okay, the problem is there, but we need to get out from this situation, and hopefully we are very, very optimistic. We already opened the laboratory since 2 weeks ago. Even just 1, 2, 3, 4 students is coming and try to do everything that we missed on this. You see, the skills, the psychomotoric that we need to do on the device, on the apparatus, on the equipment. So yes, we encourage them, because for some reason we know that this new era in the pandemic situation since last year, we have already known the comfort zone, the new comfort zone. We just stay at home doing nothing. For some reason, I don't need to change the clothes. I just need to stay on the screen, and then that's it. How easy to live, but we left something problem behind. The student can't do anything with the hands-ons, can't do anything with the psychomotor things. That's why we need to encourage them to let's come back to the university. Whatever your comfort at home, this is what you need to do on your skills. Whatever the cognitions, like we need to understand about the classes, we need to understand about you can do online. There's a lot of abundance materials on the internet as well as on the literature. But on the other hand, you need to do something with your hands on the laboratory, on the research. So that things that we need to encourage them to come back. We can't back completely as what we had in the previous before COVID-19, because yeah, we're just doing classical teaching as conventional way. We are talking, you're listening, you write down, take some notes and do the assignment. But now all of the materials are abundant on the internet. You can get access very easily. But then again, we need to emphasize that students come back. You need to do something, your thesis, your research, you need to capable on this. So I think when we had a discussion with couples of the collaborators, whatever, in UK, in Australia, and then I think it's completely similar as what we had in Malaysia. That's yeah, we can't do these things like this all the times. We miss couples of things. Yeah, that's the thing. So in this activity, we have a good agreement that we need to encourage the students. I think the participant here is huge. 66 is, yeah, both sides from Malaysia and Indonesia. We can remind and remotivate the students that we need to do something from this COVID pandemic. I think we are going to end up with something interesting after COVID-19. This is my optimistic. I hope all of the staff, all of the teaching process will be coming back normal, whatever, and being more productive, because cognitions we can do anywhere else, but your skills you need to do something here. And we're just thinking about how to improve and develop the facilities to get more easier for students to get hands-on with this psychomotoric skill. So that's from my side. If you want to say as well to our students here, it's very, very prestigious. It's very, very thankful, and I think that's a bit more valuable. Okay, the information about the research are important, but your motivation, how to do research, how to do teaching, accordingly, that is the first thing you need to take into account. That's from the student point of view. Okay, again, thank you very much, Professor Kalai. Whatever we are going to have, I strongly believe that Dr. Riris and some colleges, Brother Alfian, Ms. Osma, they are very, very eager to do the collaboration, to do the research, because they're young. We are not a lot. We just how many Dr. Iris is that just 9 staff in biomedical engineering, right? But yes, they are young and very with a high capacity. So I like persons and people in biomedical engineering. So yes, we are ready for any collaborations. Thank you very much, Dr. Kalai.
Thank you, Prof.
Thank you very much,
It's a pleasure.
Dr. Heri.
And I think the Alangra Faculty of Science and Technology is very lucky to have a dean who really care that the students need to come back and do hands-on. And this is important for their knowledge and also their future to bring the next generation to the research, because country like us, Malaysia, Indonesia, we are still very young in research. And it is very important to start with the high quality work and a realistic work like what I mentioned just now. Of course, we have a lot of toolbox now, but the toolboxes are just to help us to establish the initial work. But the actual work had to be in the laboratory, and they really need to derive the outcome from themselves. And this is where we become the contributors. Otherwise, we will be always on the surface and being exploited when it comes to the detailed implementation. I think we really saw that during COVID-19, how we were struggling to solve our own country's problem. I think most Asian countries, even Japan and Korea, is very quiet. And you saw their prime minister, how they are reacting compared to the Western world. I am very impressed with New Zealand. You know, New Zealand is never much highlighted, but they managed it very well. And they had a lot of findings from their research, which they can use to solve the problem during the pandemic.
Yeah, that's they well maintains all of the situations, whether the cases are increasing or decreasing, whatever they are outside. It's a bit different compared to Australia. Australia is very huge and they have a lot of complexity. So it's kind of they hardly control this pandemic COVID-19 situation rather than the New Zealand. I agree with your idea. Okay.
Because Australia, I think their major problem was their immigrants.
That's right. Yeah. There's
too much, the percentage, too many Asians there.
Yeah, sure.
So that has caused the blunder in Australia.
Yeah,
I think they have realized now. I think they're going to stop their what we call it, the PR awarding and all this.
Yeah, and it's getting stricter and stricter, a lot harder, rather than just back to 6-7 years ago. Yeah.
Okay, thank you, Prof. I think there's some questions from the students.
Yep, not a problem. So I would like to say thank you again, and I need to leave because I need to do other meeting. Thank you very much, Professor. Have a nice day and enjoy all of the talk, students. Thank you.
Thank you.
Thank you, Dr. Heri. And before we continue our Q&A session, Dr. Kalai, I would like to remind all the participants that haven't not filling the attendance list, please filling the attendance list in the comment or in the chat link, and so we can send the certificate after the session. And now we have a few questions from Muhammad Kasif. Good morning, ma'am. As you know, the wireless signal around us are growing day by day. Can this signal cause interference while capturing a biosignal using wireless? If yes, then how we can prevent from this interference? Because the wireless signals are everywhere. Thank you. Maybe how about your opinion, Dr. Kalai, about the interference signal?
Okay, thank you, Doctor. Thank you, Kashif, for the question. I think it's a very interesting question. In my own experience, okay, number one, we need to know the device frequency of the wireless, what technology they are using, and what is the frequency that they capturing the signal. Like early days, we used to use ZigBee in the hospitals because ZigBee's range doesn't interfere with other devices in the hospital. But today we have a lot more options like LoRaWAN, NB-IoT, and many other things. Depends where we are positioning. For example, if you're in the ground, ground floor, underground, hospitals there's also undergrounds where we do signal tapping. So we really need to understand our device and also the interference around us. Another thing that I encourage to do is to test what are the interference or wireless which is available before we even do our setting in that place. And normally our data recording setting, it will be either in the lab or in the hospital or in the clinics and so on. So it is very good to do the measurement and we know exactly what is the strength of the other interference around that area that we are tapping. Two good things, if let's say we can't avoid, we know, so we can remove them. That's not one. Second thing, we can choose the best location with the minimum interference. So this could be the best solution at this moment. And when I'm a little concerned about when patients do it at their own home. So it's good that the device comes with the baseline indication. So when the baseline is recorded, then we know at certain extent how to do the baseline. Now either we package it into the device as a protocol, or we add to like in some of the device that like the CPAP machine, the individual will come to the home to do the setting for the first time. The companies actually have that protocol. So when they come, they will identify all these limitations and then they will advise patients accordingly in using this device. So these are the approach at this moment. And with the people who are in the communication industry, I believe they will definitely be looking into all these limitations, and that a lot more research and work is going on with 5G now, and all those other more and more wireless device coming along. We definitely would see some input from them, like what they came up with LoRaWAN and NB-IoT now, different applications. We hope in the future there will be a special frequency allocated for the medical devices with minimum interference from other frequencies. So this is what we are looking forward for. And we hope the communication engineers in the telemedicine and in the area of tele-rehab and all those researchers will definitely look as a solution for this, right? I hope I've answered the question.
Okay, Doctor. So we need to choose wisely about the wireless device that we want to use, right, Dr. Kalai?
Yes.
And
yes.
also the other, maybe the additional question from Kasif, can we use PPG signal for user authentication? And what do you think about the accuracy?
Okay. There is possibility, but it's a very challenging, because as what we know, our PPG signal change with age. All right. So in terms of using it as an authentication signal, it maybe there is good because it has to be updated as the person's age change. And from my own study, the changes take place every 5 years.
Okay.
Every 5 years. That is promise that person didn't develop any CVD disease, cardiovascular disease or cardiovascular risk factor. If the person develop cardiovascular risk factor, the changes even will be faster. Okay. So, and also, for example, for people who have diabetes and they have unstable sugar, the sugar level changes every now and then definitely the reliability is not there. So with us considering all these, and also heart rate changes, the person must be at a rest condition to have a very identical signal. That is one thing. But it may be done with other further processing, but not directly on the signal pattern, but some features extracted from PPG. So that may apply, we can explore, but as at now, there's number of suggestions, especially there's suggestion from China to use PPG as the biometrics authentication. But as at now, there's no real reliability that we could see. But it can be used in certain needs, probably. But yeah, the research is ongoing.
Yes, okay, Dr.
Right.
Kalai, thank you for your response. And then another question from Natania Isela. Good afternoon, Dr. Kalai. I'm really curious regarding how could we use biosignal processing in this pandemic situation, especially regarding handling COVID-19 patient. Thank you in advance, Dr.
Okay.
Kalai.
I think so far I've seen about 30 papers published in the last 20 months using PPG in addressing COVID-19. Some of them use the RR. They actually derive the RR value and look at the heart rate reliability to predict the presence of either the person has a symptom of COVID-19. There is papers which has looked into the physiology changes by calculating the area under the curve under the PPG wave itself. And they have used that as an indicator that is a physiological change, especially in the depletion of the vessel depletion, which is one of the indicator expected there, because they expecting COVID, when the patient has COVID-19, they deplete in terms of their, the symptom is quite similar to dengue, where the vessels deplete. So they also use respiratory, they use the DC signal to look at the respiratory stability, because as what we understand, PPG has got AC and DC. So the DC can also use to predict the respiratory condition of the patient. So there's quite a number of people which has looked into that. So the potential and possibility is there, but what is important now, we need to get reliable data. My own challenge in Malaysia, how can I access the COVID patient? Because I need to access them from the early stage to the recovery. And we need their daily data, and we need at least 4 times or to 8 times daily data. With the current condition and the current management of COVID-19 and the fear people have, I don't think hospital is going to allow any kind of exploration.
Yeah, I think the data is still limited for the COVID-19 patient, Doctor. And also several data sets maybe are openly in website, maybe like respiratory data, like maybe breathing and coughing. But I'm not sure, is it really possible to do the respiration signal? Because as you said before, it's a DC signal, there is so many noises.
Right.
And maybe do you have any suggestion to remove the noise? Maybe.
Okay. For DC, we still have a good filtering techniques for PPG to remove those noise. We can get quite a clean noise, clean signal for DC. That's not a real issue, but the issue here is to tap that signal in COVID patient and access, because like what we know, we don't want the touching part. And this is still, even is a non-invasive, but we need to use it on patient. They may, which I think the papers that published, right? It's mainly from Europe. I see a number of papers from Europe and US, where they have good protocols. Italy have done a quite number of study, because they are the first one to really suffer from that high number of death, and their hospital protocols has really gone on very good. And being European, they know exactly during disaster is the time to do a lot of study.
Yeah, I think.
And get a lot of good solution. And also being European, they take risk. For them, science is more important than their life.
Yeah.
A lot of them, we know, right, how they sacrifice their body. And I still remember when I did my PhD, I wanted to get data of my left ventricle to as an input to my model. And I was like high and low searching, how can I get this data? You know, that's no way, who's going to let me take their left ventricle signal, right? Yeah. Then I was searching and searching, finally I found a paper from 1968, where they actually, one of this guy donated his body, and allowed the researchers to open up himself while no sedation given.
Yes, I
And
think.
finally, actually they tap the signal from each part
Mm.
of his arteries, different arteries, and then from the large arteries, small arteries, medium arteries, muscular arteries, and then the heart, different parts, different chamber. And this was recorded and the signal was in their library.
Mm.
So then I had to write into them, and they gave me the printed version. They only had the printed version, you know, at that time they didn't have the digital version. And I did the tracing and I did age detection and converted that into a signal and then fed into my model, and my model worked. Before that, even I tried to do so many different mathematical equation to develop that shape, you know. It didn't work because when we use the mathematical shape, the properties are not there.
Yeah.
The properties are not there. They are like blank, you know. Yes,
Reality.
right. But amazing, imagine it is just it is on paper.
Mm.
But when I traced and detected that age, I managed to do the detection 99% accurate. Yes, because I put that age detection, a close point, you know, I took the time to do it. But it was interesting. The moment it was the original tracing and the model worked.
Mm.
And I was like high and low more than 2 years.
That's
I was
quite
like almost gave up, you know. I really think that I'm going nowhere. This is not going to solve any problem. And it's from Netherlands.
Mm.
I found it in a Netherlands language thesis. I translated the thesis using Google Translate at that point of time and start understanding what they did, and that's how I wrote to them. I managed to get the input. So I think it's very important, such experience and exploration, where students, you know, like when you want to do something, you should have that courage, and you must believe what you're doing is correct. You're not like plugging something from the air, and you are really working on something realistic, and there must be a source that can help you.
Mm-hmm.
And I always believe in learning. When you are sincere, that somehow, somewhere you will get the door open for you.
Yes.
So this is real beautiful experience of mine, where I really solved my model. If you could see that my PPG, what can be recorded from our finger can actually be plotted out from my 10-element model. And that was a dream come true for me. And until today, I'm still looking for a student to do in the next step, because I want to develop that. Currently, my model is developed in PSpice. So it's very hard to do the simulations, you know. It is like, it takes a lot of time. So I would like to translate that into a MATLAB simulator and designed it, and we could play around the parameter very much easier. So that actually the model can tell you if you're a diabetes, what we can play around with the shape. I feed in the diabetes patient shape, and then I can trace back from the model what is the large arteries compliance, resistance, and the velocity value, the inductance value, and relate it to the vessel compliance, vessel resistance, and the velocity of the blood, the thickness, you know, which again relates to hypertension, diabetes, and hyperlipidemia. So this is how actually the whole model is developed. So it will be very nice if we have a keen researcher. Maybe we can even do explore among your students who has who are keen to work on like this. Then we can have an exchange program. They can spend some time in Indonesia and some time in our lab in Malaysia, and we can work together. And I think that's going to be really beautiful to have that kind of collaboration.
Experiment as well for students. I think
Yes.
students need take more courage to do that, Dr. Kalaya.
No, I think it is the exposure, doctor.
Yeah.
You see, from my 26 years now teaching, experience, and being a student myself in Malaysia, and I did my entire education in Malaysia. You know, I never, from my preschool to PhD, I did it in Malaysia. And when I went for my Erasmus attachment, 5 weeks in Spain, what I can tell you, we are not far from them. The only thing what is far is our dedication.
Yeah.
Dedication on both sides, on the student and also on the lecturers. You know, we cannot blame 100% on students.
Yeah.
It is both of us, how we look at our job. See, when I was there, one thing I was very impressed was their lunchtime. See, there, people don't eat lunch in cafe. They have what we call it, a room, you know, for postgraduates and lecturers. They have a room where they have microwave, they have fridge, they have the coffee machine, their food machine, all inside there, and nice tables. And everybody come in the morning and put their food in the fridge, and then they come during lunch, eat it up, and they start sitting down and eating, you know. And every day we go, we meet different people, we talk about different things, we share our research, we ask, hi, hello, how are you? You know, and these actually also, this relationship solve a lot of problems and encourage research to a certain extent.
Yeah, I think that's good, and also motivating each other as well.
Yeah, I think first we need to set up such a place, you know,
environment,
environment for students to have this type of discussion, especially on the postgraduate students.
Yeah,
because they need rest and they need some break. So during tea time, we go there again at 4 o'clock, and then when we stay back, you know, 8 o'clock for dinner. Most of the time I'll come back at 10:30 at that hour, you know. I go in the morning at 9 because there's so much to do and it's so fun.
Yeah.
So these are also important, especially in biomedical engineering, like I explained just now in the starting. It's an interdiscipline and transdiscipline work. We really need to hear from other people's experience and technology, and sometimes just click, wow, this guy is doing this, I can apply this technique in my work. I should go and see him, you know, sit down and ask, like OR, you know, operational research. Operational research techniques like linear programming, optimization, all these things has got a lot of application in our work.
Yeah.
So somebody with OR background will be very helpful for us. And also I think you should encourage, if OR is offered in your university, in other faculty, you should encourage your postgraduate to go and audit that paper.
So they will do another, will have another perspective from them.
Yes. And I did my operational research when I was undergraduate student as elective paper. And that is actually a big help throughout my life in most of the research work and also all the applications that I do.
Yeah.
So I think that can be a good encouragement for the students.
Yeah, I hope we will have such a good environment and also opportunity to have
I think we need to fight, Doctor. We need to fight. Like what your dean said just now, yeah? I think, you all are young and energetic, and 9 of you be together to fight it out. You know?
Yeah, we have to fight.
If you need any help, you let me know. You want to do proposals to fight for rights, let's do it. You know,
okay,
we can do it together.
Thank you for your help. Yeah. Maybe we have another question, Doctor, from Mr. Alfian. He's also one of our staff in biomedical engineering.
Right.
Please, Mr. Alfian.
Okay. Can you hear me?
Yes. Yes.
Okay. Okay. Good afternoon, Dr. Kalai. It's nice to meet you. Yeah. My question is about the noise in the biosignal processing. Right. We know that we have a lot of problems because of the noise in the biomedical signal. Is it better to have a really good device that has minimal noise, or we can just rely on the filtering process in the analysis? Thank you.
Okay. Thank you, Doctor, for a good question. Of course, a reliable device with good noise filtering inbuilt is the excellent solution to this, because how much we do at the filtering, we will definitely lose some of the properties. even our filter is like really excellent from my experience. There is tendency to lose our important features. So the first part, of course, a good reliable device with inbuilt noise filtering is an excellent approach. We cannot deny that. That is why whenever a medical device is being developed, it's the FDA is so hard on that.
Yeah.
Yes, because otherwise the reliability, the reliability.
Continuing the question of Mr. Alfian, Dr. Kalai, maybe a wireless device like EEG or maybe EMG, there is also a delay in the signal processing. And is it also became an interference for signal processing, or maybe the delay is also okay for the medical devices? Like maybe, well, because it is wireless, then when we want to send or receive the signal from microcontroller or maybe the PC, there is also a delay included.
Okay, doctor. This depends on your application. How critical your real-time data capturing. If that data is going to be used in a surgery, for example, in a surgery room, you are capturing some signal and the doctor is going to depend on your signal to do the treatment or the surgery. That has to be timely. That's no negotiating, right? But then if your data is being captured and being saved and for further processing, and you have a luxury of time, and it's like a near real-time needs, or you can, like, you're going to deliver the results after a few hours or the next day, then definitely the delay is not going to be a factor that will affect the results. But you must make sure that your processing is correct, taking calculation into calculation your delays. Especially when you have a synchronized more than one data that you are synchronizing. For example, you are capturing PPG with ECG, or EEG with ECG, or ECG with EMG. Those type of things, and you must be very, very careful in looking into your delay, calculated into your processing. Otherwise, we may give some,
perception,
wrong perception for the patients. So these are the importance. At the moment, we have a lot of limitation. Even though we say we have 5G, right? Sometimes we realize that 5G is 5G, but our laptops are not able to cope. Our devices are not able to cope, and even our mobile and so on. So it is beautiful to hear and believe, but when it comes to reality into biological signal processing and so on, it is not as easy as what we are hearing. But of course, the social media data, text data and all that is much easier. Even the images, which is not medical, is much easier. That is why I think if you really carefully analyze and look at LinkedIn offers and all those things, scholarships, everything, that's not much in biomedical engineering. It's very limited. It's pretty quiet still, right? And all of us are also not very brave to share or to say that our findings. We still have a lot of doubts. Are we doing things right? And especially being Asian, I think we are extra careful in all whatever we are doing. But I think that is good because we want to be careful and we want to ensure quality. And I think our most of our limitation now is to get a good research students. So we really need to work on that in our undergraduate program.
Thank you for your insight, Dr. Kalai. Is there any question for the other participant, maybe?
Maybe I want to ask Dr. Kalai.
Sure,
Thank you very much, Dr. and Dr. Kalai. Back to the when we use the data set from internet, Dr. Kalai. In the fact in this pandemic condition, mostly our students prefer using the data set on the internet, and we allow them because of this pandemic situation, Dr. Kalai. So what is the pros and cons when we use this data set, Dr. Kalai? Because we don't know the pattern, how the expert decided the pattern, and we already got the describe or annotate the pattern. This is the something like a tumor or not tumor, and we don't understand what is the pattern of the image or the signal, Dr. Kalai. So what is your point of view of this condition, Dr. Kalai?
Okay, thank you for the question, Dr. Riz. In my work, in my research, most of the students will work on the data only for a pilot, right? For pilot study to establish the first fundamental, and we understand the limitations, so we can establish our protocols better for data recruitment. So during the pandemic, of course, that's lots of things we have given leeway and space. But if it's an undergraduate student's work, I'm good with it, because that's okay for them. Because for undergraduate, they need to understand the concept, and for example, they will like focus in any one particular aspect of the entire work. For example, just now I had the 4 blocks, right? Pre-processing, the noise removal, and then the processing, the filtering, design, and all that. Then we have the feature selection, feature extraction and selection, and finally the classification. So when it comes to undergraduate, we will normally give 1 block only to them. We will not ask them to do the end-to-end process like the master's or PhD students. So for them to test their algorithm for classification, or algorithm for their feature extraction, or the noise removal, or digital filter design, fine. They can proceed with the data from the open databases. But for masters, I really hope and wish they have the courage, and they have the, at least they can, if they cannot go to the clinic, I'm good with it. But they can do the data collection in the hospital, so in the campus environment, since we are coming back and all that, even the home environment, at least they can collect some data. The experience of collecting data using the device is very important for them in research. How do they justify, right, that part when they want to go, and after their masters, they may be working in a hospital, or they go into PhD, or they even go to the industries to do their career, to develop their career. How do they really justify this in those environment, the work environment, if they don't have at all hands-on experience on using and collecting the device? How do they know the challenges? Even they can do it at the laboratory level. Among us, we become their subjects. Unless they're doing a disease, then it's different, it's going to be really tough. In that case, like what doctor did, we can collaborate with the universities and then get the real data. So that is another approach that we can assist our students. And definitely they have to collect some data with the device for that experience, but then they can get the real data from the clinic for the disease that they are working on. That's going to be another approach. I think what you're doing is really right. So if you have further requirements, maybe you can connect to us. So then I can connect you to the right team, maybe the teams that I'm working with from India, Sri Lanka, Australia, and all that. They may have more data, so that we also can link through them to get more data.
Nice, very nice. Yes, occasion, Dr. Kalai. Yes. We can design some of project maybe Bu Asma.
Yeah, thank you, Dr. Iris.
Thank you very much, Dr. Kalai.
Last question, maybe Dr. Kalai from Kolia. This is another curiosity about the PPG. Can PPG signal detected by smartphone camera? Because as long as I maybe know about the PPG signal, always place in separated device. And if it could, how much the accuracy by using smartphone camera to obtain PPG signal? Thank you, Dr. Kalai.
Thank you. All right. We have done 2 projects with the smartphone, capturing the PPG signal. Of course, in smartphone, it captures by frame. So it is actually image. And then from there, we do further processing to get the process to what we want. So far, we find it is accurate for heart rate. That is quite reliable. The heart rate extraction is reliable. Respiratory was not very good. We only achieved 60%, but physiological have challenged. We have challenged. What we call it as pressure. We could also do pressure for the SBP and the diastolic DBP. That is about 75 to 80% accuracy. But heart rate, we had 92, 93% accuracy. Heart rate is the best. And we SpO2. We could also do SpO2. But physiological is definitely challenging. Like what I told you just now, when we trace it, it doesn't have that penetration, I believe. So it's not capturing 100% like what our optical device, the pulse oximeter ability. That is where we are not able to do it. It looks empty. When I start processing it, I cannot extract any information from there for the vessel level behavior. It doesn't penetrate to vessel level behavior. Yes.
We need to make sure about the experimental method, like Dr. Kalai.
Yeah, and also I think the camera accuracy and camera capability.
Okay.
The pixel values and
also the lighting.
Yes, yes. The challenge is because I always consider the ability of this project to be implemented across to public. My question here, everyone is having different model. If I developed an app in this, how much time and updating I need to do? Because in no mobile app, right, it needs to be updated together with the upgrading of the software of the application, Android and also the iOS. And number 2 is the hardware itself, hardware limitations. And every manufacturer is fighting each other, and they're doing magic. So are we really ready to do this? That is why in my work, I'm using mobile phone images more on image processing, because I want a JPEG. I rely on the JPEG technology. I don't rely on the camera or the device. So I believe as long as they save it into a JPEG file, then the reliability is there for me to do the further processing. So signal related work, we try to avoid smartphone, but image related work, we try to more and more on smartphone, like the skin disease, ulcer,
Right. Okay. Thank you, Dr. Kalai. Maybe to sum up, maybe also for motivate us to do more research in healthcare technology, Dr. Kalai. Maybe for your based on your experience, how far actually we for how much step, like you said, maybe TRL 1 until 8. How long is the process maybe for experimental or maybe laboratory research to become public ready for the medical device that already used public?
Okay, doctor. This is a very challenging question.
It's still too far for us.
It is again, the most important is the team. Okay, my own experience. I started in 2003. My PhD work, which is not able to commercialize until today. But there is work that we started in 2014, 16, It's already almost there to be published. And we have one more device now.
Okay.
It is less than 3 years. So it is all experience and a good teamwork and the reliability of the team members to move in this. If the team members keep on dropping out, that is the biggest challenge.
Yeah.
And also the what we call as the sincerity and integrity in the entire work. It is also very, very important. If you first, I will advise you that you must have a good team. Even it's 9 of you, how are you going to divide yourself? Maybe you have different direction. Some of you may work on image. Some of you may work on signal, BPG, ECG, EMG, and all that. So how do you intra and inter working into these projects?
Yeah, I think it needs to be
the important thing is the collaboration, Dr. Kalai.
Collaboration, yes. Next is collaboration.
Yes,
and
to
also the direction. Yeah, and the
Yes.
direction, doctor. The direction is very important. And I also believe another most important thing is the openness. Openness. How much we are being open in our problems. Yeah, because every problem has to be settled as soon as possible.
Yes, but the honest research, I think, Dr. Kalai.
Yeah.
Yes, if there is a problem, so be honest. To be honest, yes.
Yes, honest. Yes, that is the most important. Students need to be more honest on this part, because otherwise they will be wasting a lot of time. For me, it's very simple, doctors. You come to the university to learn. So we don't expect you to know everything. If you know everything, then we don't need you to come to the university. Right? So for them to be with us in the university is to learn by the guidance. And what we expect from them is hard work and also the effort and the time. My expectation from them is the time. Time is their investment in research. They're willing to spend the time in the research, then we can teach them. We can guide them. And it's very good, doctor, if you can practice a boot camp. These boot camps will actually solve a lot of problems. Like you do a 3 days or 5 days boot camp. And a particular problem, so we can share later some of our boot camps. I can explain to you how we do a boot camp will actually do a lot of change, and also time to time training in the research group. For example, we run a statistical course for 2 days.
Yeah, it's very nice, Dr. Kala.
Yeah.
Yeah, I think our students is more attracted when they do some hands-on and experimental directly. Then we try software from the dataset on internet. I think it's not more challenging for them than they do experimental.
Correct. We can even do a bootcamp where they collect data. Like I used to last time when in my first batch of students, we were doing work mostly with community. So I even take the whole team to go and collect data in like villages, in suburbs. We stay there 1 night, 2 nights, and then we put a boot camp. We set up the entire station. We collect data. All those activities are very, very interesting for students, and they learn a lot. So we can even have those type of activities where the learning process is faster.
Yes, right.
I think for Indonesia, it's going to be very beautiful. You have a lot of villages. And I think people there, when I went last year to pick up my helper in Lampung, they are so beautiful. They are so like easy to listen and come and collaborate, to help each other. If you put a boot camp there, I think everybody will come. It is not difficult, Yeah, so that is going to be very interesting. And sometimes you can use your students to arrange it in their own village. That will give them a lot of confidence.
confidence.
Yeah.
Yeah. So that will also bind them to success. You know, they want to work hard to improve because their own people have seen him or her in action, you see.
Yeah, maybe you can share maybe some videos, Dr. Kalai, from this
Sure.
bootcamp. Yeah.
Right.
Yeah.
Definitely.
Thank you very much.
All right.
Thank you,
Okay.
Dr. Isis.
Maybe I've exceeded 20 minutes,
Yeah.
keeping everybody during lunch.
Okay. I think I think
Everybody's-
this event is about to come to very end, Dr. Kalai. Thank you
Yes,
for
I hope it really benefits all of you.
Yeah, I hope so. It's really interesting knowledge you share. And before we end this session, I would like to invite all the participants to open the camera and we can take a picture together. Maybe please open your camera and then we could take a photo together. Student. Yeah, okay, thank you for participant. I will start capturing from the slide 1, maybe. I will wait for the others to join to open the camera. Thank you. Okay, I will start from the slide 1. 1, 2, or maybe a few more. Okay. 1, 2, and 3. Wait a minute. And then the next slide. Please get the camera ready. 1, 2, and 3. Okay, thank you for all participants and your time as well. We hope you all can get the beneficial from this today lecture. And also I would like to thank you once again for Dr. Kalai and also all participants from University Kebangsaan Malaysia for joining this event. I wish you a pleasant day. Thank you and see you in the next event. Good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you.
Thank you very much.
Thank you very much, Dr. Kalai.
Thank you so much.
And for all the participants, thank you very much.
Thank you, everyone. Thank you.